Hello everyone. Today we're going to look at multiplying binomials and converting from vertex form to standard form. So the vertex form that we got to be familiar with by just looking at all the different transformations. We're going to look at how to convert that to standard form. Just be able to convert between the forms is good. To look at multiplying binomials, I'll remind you of, we'll go back to, maybe you haven't seen them, hopefully you have, algebra tiles. And they're good for representing this kind of stuff, right? So you can help visualize what 2x squared plus 3 looks like, and specifically why it's not. I'm going to say plus y it isn't equal to like 5x would be a common, or 5x squared or something like that. People might say by accident, right? So that's not true, and algebra tiles help you see why. They help you figure out different ways of representing same polynomial. You'll see that in the examples we do. They help you figure out the sum of two polynomials is. They help you figure out the product of two binomials. This is the big focus for today, for sure, because our lesson's about multiplying binomials, right? So product of things, it means multiplication. So that's what we're going to be looking at. So just to remind you what algebra tiles are, they're little rectangles and squares that represent the polynomials. So if we're talking about an x squared tile, for example, down here, x squared is literally a square, and it's x by x dimensions, right? So x times x, the area of it is x squared, and so that's your x squared tile. The area of it is x squared. Up here, we have an x tile, and its dimensions are x by 1, so its area is also x, right? It's an x tile, and its area is x. Notice that the length of x, the size of x, is a variable, right? So it can be any length. This is still an x tile down here, just a different x value, and there'd be a different x squared that would correspond to it as well, that would look like, this. So you can't trust or almost like that anyways. You can't trust the length of x to say, oh, it's, any kind of connection between the 1, which is a fixed length, and let's go back to the way it was here. So you can't trust anything that looks like a connection between the length of the 1 here, right, versus the x, right? You can't trust that look comparison, right? So just like, no, don't say, oh, it looks in this case like the 1. If we did another one of these here, if you did the 1, it just happens to look like 1, 2, 3 of them, let's say. But that doesn't mean x equals 3 necessarily, right? It's just representing a variable. All right, so those are your tiles. Oh, and the 1 tile is a 1 by 1 tile. So obviously the 1 size has to correspond to the 1 there, right? And so on. So notice the area of that one's 1 times 1, so it's the 1 tile as well. All right, so if we're looking at all of those tiles, the question is what polynomial, what algebraic expression, like whatever the equation might be, or it's not really an equation at this point at all, because there's no equal sign. It's just a thing, right? If we're saying that this stuff, all of this stuff adds up to, say we added this all up. Okay, so if we added all of this up and said, okay, that's equal to 13 or something like that, then then we'd say an equal, there'd be an equal sign here, and now it's an equation. Okay, but the polynomial itself, to group it like a polynomial, I shouldn't have had that answer down there exposed. But you have your 2x squareds, right? So they're going to combine, and that's what we can refer to as combining like terms. Okay, so 2x squared tiles gives you, of course, 2x squared as a polynomial that represents it. So hopefully you can the idea is to recognize that 2 of these is just like saying 2 of these pictures, right? Same thing for the x tile. There was 2 of those, and then there was 4 1s, and so technically this is like 4 1s, but of course 4 times 1 is just 1, or 4 times 4 and 1 is just 4, I should say, right? And again, notice that, you can't combine 2x squared and 2x and say like something like 4x or whatever. They're not the same type of thing, so they don't combine. Okay. So this version of things would be an equation. This version, just the blue version, would be, an algebraic expression or a polynomial or whatever you want to call it. So algebraic expression or polynomial. Just keep the term equation for when there's equal signs. It's just a definition. It's just a name though, so it's not critical really. Just knowing what's what is nice. So we're going to look at the distributive law as well. So the distributive law is just, this three of that stuff literally means three groups of those things. So three of the 2x squared plus x plus 5. So think of 2x squareds plus x plus 5 ones. That's that polynomial. So you're going to have three of those things, right? So if you have three of those things, then you have all that stuff, right? So for collecting like terms, you can see we have 1, 2, 3, 4, 5, 6 of the x squareds. 1, 2, 3, 4, 5, 6 of them, right? And so you're going to picture 6 x squared tiles, which of course can be just written as 6x squareds or 6x squared in the polynomial. And then we have 1, 2, 3 of just the x tiles. 2, 3, I'm missing one there. Weird. All right, so let's just clone that thing. I'm copying and pasting, making lessons. Sometimes I miss pieces, I guess. So there's 3 of those guys. 3x squareds. See if it was right in the end here. Nope, never caught it when I was making it. So this is 3x. And then we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, right? So we have 15 of those. So 15 ones, of course, just looks like that, right? So there's your polynomial in the end. So yeah, that's the result we have from that. The math process of that I need to show a separate slide. I have in this slide here. What's going on here? Auto hides on for some reason. I have there that it's just like the result using distributive law, but I need to show the distributive law still, which I'll do right here. Okay, so the distributive law, when you do 3 times 2x, you have a 3 times a 2x squared, sorry, not just x. And then you have a 3, this next arrow right here is a 3 times an x, and then a 3 times a 5. I'll just show those steps. People wouldn't necessarily show that every time. You might just cut right to the result from that, right? So 3 times 2x squared, you can tell 3 times 2 is 6. So we get 6x squareds, just like in the pictures. 3 times the x gives us 3x, and 3 times 5 gives us 15. Boom, done, right? The algebra works out and matches and so on. The picture matches the algebra, okay? So the distributive law right here is a nice, powerful mathematical process of getting what makes the answer that makes sense, right? Answer that matches reality of how many x squareds and x's and ones you'd have. Okay, so that's algebra tiles. What we're going to be doing, this is a bit of a review here now, but if I just chose some tiles, right? Let's just do something like whatever, something like that. What polynomial would be represented. And so you look at that and say, okay, well, we've got, just move them over a bit more so that we have it distinguished from the source. This is just the source of them, right? So that's not one of the ones we're talking about. Those are my infinite cloners. So we'd have, 1x squared. That's understood to be a 1x squared, of course, right? And then we'd have 4 x's, and we have 2 1s. So do 4x plus 2 1s. The dotted stuff's just sort of the understood stuff. In other words, we're saying here x squared plus 4x plus 2, right? So one of the other things we said we wanted to show was how we can represent things in different ways or as a sum. And so that's coming up here, right? Can we represent this polynomial as a sum of 2 polynomials? And be like, yeah, sure we can. We could maybe group this thing as, let me just get a copy of all these guys. Clone all those, bring those down, and we just group it into 2 groups, right? So maybe you have 2 groups like that, right? In which case you can tell that this polynomial here, since it's the same stuff, would be equivalent to the original. So we'd have what, an x squared plus x plus 1 as a a thing, an algebraic expression or a polynomial, plus 3x is plus 1. Right? Those are 2 separate polynomials that obviously are equivalent to the original, right? So this would be equal to the x squared plus 4x plus 2, right? And so if you were trying to show that that was true algebraically, you started with this, you would have collected like terms. You would have said, okay, well, we've got the x squared is only the one of them. There's an x there and 3 more x's there. So we've got a grand total of 4 x's. And then we have a 1 and another 1. So we'd have 2. So I'm just trying to show multiple ways of looking at things and the kind of algebra steps that make sense and try to help rule out the algebra steps that do not make sense. For example, saying that this is equal to 6 or 6x or whatever, that's really quite wrong, right? So you don't want to do wrong stuff because you get wrong answers. There you go. All right, so finally on to the main event here, multiplying binomials. And so we're going to use the fact that area is a concept as part of this to do this. And so we're going to look at this right here as x as a dimension, right? So we're thinking of this as an area equals a length times a width. And so we're going to make the length and the width be x plus 1. So an x and a 1. So that's a dimension there. These tiles aren't quite the right sizes, but it still represents good enough, right? So if you make them a little wider. And then along the side here, we have an x plus 4. So same deal here, make that one a bit wider so the widths match. But we need 4 here. So x plus 1, 2, 3, 4. So what happens then is you can see that this area, this area here, this area is that, right? So that area equals the x plus 1 times the x plus 4 because the length times the width, right? That's what this is, length times width, right? And so the stuff that fits in there is the answer. So there's an x squared that fits in there. Just calibrate it so it's the right length. So I didn't notice that the x's weren't matching either, or because I widened them to make them match the 1, I guess, right? I really should just shrink that one little 1. Easier fix for the lesson as a whole. And then we can see that an x would fit in there. Again, I'll just rate it so it's the right 1 size and x size and so on. I don't think we need to be too fussy about it. And then you can see that an x would fit in here. So I'll just make that good. And then I'll just clone that one a bunch of times. Just use the keyboard for that. Control D is the hotkey. Oh, one more. So there's space, like things that would naturally fit in that area. And then the ones would naturally fit in here. If everything was calibrated to be the right x and 1 and 1 all the same. All right, so what we're seeing from this is that the area is equal to x plus 1 times x plus 4. And the answer is clearly an x squared and 1, 2, 3, 4, 5 x's, right? 1, 2, 3, 4, 5 x's, and then 4 ones, which is the result of the polynomial. So this is equal to that. Okay? I had this lesson geared so that someone could do this on their own more so, and there's your same result, right? The x squared and the 5x's and so on. All right, so if you tried it on your own and then checked the answer and so on, you have some feedback as you go, but I'm doing the videos now, so we're good. Then the math version of this, that's the goal, right? Or mathematics process. So when you're multiplying binomials, we call it the distributive law basically twice, right? Because we're doing binomials. Bicycles have 2 tires, binomials have 2 parts, so you're doing distributive law twice. So that looks like this, where you're going to say that the x is going to operate onto both of the other parts. So the x from the first one is going to operate onto the x in the fourth from the other one. And then the 1 is going to multiply on to both from the other bracket, right? So you're doing the distributive law twice is the easiest way to think of this. Some people talk about FOIL rule as a way to remember all the pieces, but that doesn't extend to what you're going to do later on, where you're going to have like x squared plus x plus 1, let's say, times stuff. In which case you'd have to do the distributive law 3 times. 1, 2, 3 there for that one, and then this one multiplies out and this multiplies out. So I'm not doing a good job showing that one, but the acronym for all of the pieces, if you had more than binomials multiplying, it's just messy. And so there's really no point. You can just do the distributive law twice. So when you do that, you get your x times your x is, of course, x times x. Then you have an x times a 4, and that doing the top arrows right now, and then an x times an x, there you go, and an x times a 4, there we go. Now the bottom arrows, a 1 times an x, boom, there it is, and a 1 times a 4. Okay, so of course x times x is x squared, x times 4 is 4x, x times 1 is just an x, and 1 times 4 is just a 4. And so then you can see that you have like terms of 4 x's and another x, which of course if you have 4 x's and another x, you just group them all together and say I've got 5 of those. Okay? Sometimes I talk about organizing socks and shirts, let's say, or maybe not socks, because pairs, that's more complicated. So if you had like shirts and pants, right? If you had 4 pairs of pants and then another pair of pants, you got 5 pairs of pants, right? They're like terms, so they combine. Whereas if you had, right here, 4 pairs of pants and another pair of pants, and then you have like 4 sweaters, you don't combine those and say you have 9 pant sweaters, right? Because that's just not logical. They're not the same type of thing. Okay, so the types of tiles being different, you don't group them if they're different types. Just like in organizing things, you wouldn't combine shirts and pants and say they're the same thing. All right, so that's your first model of this, right? That shows the area multiplication idea concept for the overall combination, and then the mathematical equivalent that gives the exact same result. And so we can do this again. You can try this one, show the algebra version and the algebra tiles version. So yeah, press pause, try it, whatever, come back, and let's do it here. We have actually, I've already done one of these in full, so let's just sort of pull the result in and see that it makes sense, right? So the logic here would have been, we had an x and plus a 2. Doesn't matter which one you put on the top or the bottom, by the top or the side, by the way. Right, so there's the x plus 2. I'll show this very clearly here, x plus 2. Let's jump back here and do that too. Oh, I had it there. I don't know if I did it here or not. There's your x plus your 1 and your x plus your 4, right? So here we have our x plus our 4. Just looking at the dimensions of that rectangle. And so you can see that it's x squared plus 6x's plus 8 ones, right? And then the math version gives that same result, because you're going to have an x times an x. Boom, there it is, x squared. You're going to have an x times a 4, which is 4x. And you're going to have a 2 times an x, which is 2x. And a 2 times a 4, which is 8. The 4x and the 2x, or 4x's and 2x's combine to be 6x's. So these results match, right? The algebra result that you're doing matches a very concrete, there's only one right answer. That's the problem with math sometimes for people, right? There's only one right answer. If you make a mistake along the way that's not logical, your answer doesn't represent reality. And so that's why it's important to try and get the math steps correct, of course. So another example where it's a little bit bigger. We could still do this for sure. It just gets pretty messy with algebra tiles. So you'd have an x, another x. So there's your 2x, and then plus 3. So there's your 2x's plus 3, and then we'd have 4x's. So it's just gets pretty big. And then and the problem here with this one too. We could try this, right? But the negative term stuff, you might have seen that they talk about having different colored tiles that combine with positive tiles to disappear, and it's just not worth it. Okay, so the negative tiles here, it's just not worth it. We already see that this works, so we're just going to use the math process. Okay, so basically this stuff would go away, but I'm of the mind of who cares? Let's just show that it works, right? We can get an answer. So basically, my idea is we trust this process works, and so we just do the algebra equivalent in the case where there's negatives. So let's do that. Let's say the 2x has to multiply on both of those. So let's get those done first. So we have 2x times 4x. I'm going to do that in red, actually, is the thought process step that might not be included forever. So 2x times 4x, and then a 2x times a negative 5. And then the other one, we have a 3 times a 4x and a 3 times a negative 5. And a 3 times a negative 5. Right, so that's the distributive law happening twice. And eventually with practice, you get to the point where you can just sort of do this, where you're thinking, okay, well, 2 times 4 is 8. X times x is x squared. So we have 8x squared. 2 times negative 5 is negative 10. And we have the x tagging along. 3 times 4 is 12. X tags along. And 3 times negative 5 is negative 15. Technically, you could think of this, each of these as we have the negative 10x, right? But when you have the and there, should have been a positive. We have an and the negative 10x, the negative and the positive combine, right? The negative and the positive. Let me just fix that. So that's a positive there. And the negative 10x, the positive and the negative combine to be, right? Let's just circle those to be a negative. Oh boy, it's getting worse before it gets better here. Just want to move that up a smidge so you can see the plus sign. Okay. All right, same deal here. Try and do a better job this time. We have the and negative 15 basically, right? And so we have a plus and a minus combines to be a negative. There we go. So the only like terms we have are the x terms. And so think of that as we have our 8x squared. We have a negative 10x and a 12x. I prefer to think of that as 12x's take away 10x's, right? Oops, sorry about that. 12x take away 10x's. So we have left over with 2x's, and we have our minus 15. Okay. So somewhere, some teacher is probably showing the negative algebra tile version and going on with it, but really the purpose of algebra tiles was to help help you visualize that the process works in these cases, and then go on and just do that process, and the negatives fall into place. Okay. This next example is on purpose the exact same stuff. So you can see that this stuff would be the same as before, right? So this would be your 8x squared plus 2x minus 15, just like above. And so if you have a 4 that multiplies on that, then you can tell that that would just be a distributive law happening where the 4 multiplies on each piece, right? So we'd have the 4 should have equal signs here. This stuff here is equal to this stuff, which is then equal to this. That's why it's good to have equal signs down the page on the side. It shows that you know that things are equal to one another. So we'd have the 4 times the 8x squared plus the 4 times the 2x plus a 4 times the negative 15. And then we'd get the answers from that. All right. So we'd have the 8 times 4 is 32. Use a calculator if you need. And the 4 times the 2 is 8. Hopefully no calculator there. And then the 4 times the 15, well, do the 4 times the 10 part, you get 40. The 4 times the 5 is 20, so it should be negative 60. But calculators would confirm that as well. Here's the numbers I had last time. So either I did it wrong twice or probably checked it out at some point. All right, so distributive law happening in these cases. There was just a third distributive law with that constant out front. You could, even compare to if you had the 4. Let me just own that thing. We could even do this, and it would still work out, right? We could do this first, end up with 8x plus 12. And that would multiply onto 4x minus 5. And so if you did it that way, then you'd have your 8x times your 4x and your 8x times your minus 5. Notice the 8x times the 4x would give that same number, the 32x squared. Ooh, 32x squared. And just continue on. It would be the same result. Okay. Or the 4 could even multiply it onto the rear, the last bracket, right? So, or it could have multiplied on the last bracket. Notice it doesn't. I can't multiply onto both because that would be 2 multiplications of 4, which would be equivalent to multiplying by 16, right? So it really would only go on to one of them. And the final step for this is we can use this new knowledge we have to convert to standard form. Okay, so when we go to convert to standard form, we just have to do this. We have to do the square, right? So when you do the square, that obviously just means x plus 3 times another x plus 3. And you'll see why I showed what happens with that number out front, because we need to have one of those numbers out front here like that. So obviously that's equivalent stuff. Right, 2 times the square of the x plus 3, just like it is in the first line, and so on. So we could do this where we leave the 2 out front, like we did the first time, and we'll do the distributive law. So x multiplies onto both of those, giving us an x times an x, showing that additional step one more time here. An x times a 3, and a 3 times an x, and a 3 times a 3. Now I kept everything in the exact same order as it was, but I didn't have to, and I certainly don't have to moving forward. What I mean by that is you should recognize that we have in here an x squared, of course, a 3x, because x times 3 is the same thing as 3x, and a 3 times x is also a 3x, and a 3 times 3 is a 9. And we have the minus 7 waiting to happen later on. So if I'm showing lots of steps here, we'd have x squared plus 6 x's, because 3x and 3x combines to be 6 x's. And then we have to do the 2 multiplying out. All right, so the 2 is going to multiply out onto this stuff now. Doesn't matter whether the arrows go on the top or the bottom. I just felt there was more room there, so I went that way. So we'd have, if we're ready for it here, I could do it. So I just say, okay, 2 times x squared is 2x squared. 2 times 6x would be 12x. 2 times 9 would be 18. And then we'd have this minus 7 waiting to happen still outside. If anybody in class, whenever I do that, there's usually someone that says, how did you get from that line to that line? So of course the magic would have been to say, okay, well, we have the 2 times the x squared plus the 2 times the 6x plus, I'll just leave it like that to show that I skipped a step. But I think it's reasonable at this point to do that. Okay? So your 2x squared, your 12x, and then we have the 18, take away a 7, so we have an 11. So that would be the result of that. So the quadratic in vertex form that you can tell is going to have a vertex at -3, -7, and you know the shape of it, and you have a really good idea of everything about it, really. Opens up and all that good stuff. We've converted back to this original standard form, which we know from this form is a little harder to tell where the vertex is, but it's still a form that we know and should be able to, get it in and use it if we need to. The trick later on, there's another process where this is actually the more valuable process, right? Converting that way. I'll leave that as a, how would that work kind of situation. But obviously the value of this would be, then you could tell the vertex and so on, right? So from this one, vertex is completely unknown. Whereas if you did convert to that form, then your vertex would obviously be this -3, -7, right? So this process of converting to the vertex form is definitely a valuable one. So not for today, but definitely a valuable process. So that's it. We have the practice questions, of course, on the first page as always. If you have any questions, make sure to submit them in the discussion post or just email them to me and I'll make a discussion post if you're shy. All right. Talk to you later.